in this problem, we have a pole that is supported at one end. It's attached to a building, say a wall, by a hinge. So we've got this pole, say, that's hinged at one end, so it's free to move up and down. At one end over here, there is a sign, a 10 kilogram sign, suspended from one end. The pole is 2 meters long, and at this end, the sign is suspended, hanging off the pole. The pole is, now ordinarily it would just fall down, but it's supported by a cable which is attached to the pole at a distance of 1.50 meters from the hinge, and then goes up and is attached to the wall, making an angle of 45 degrees with the pole. So this is the pole here, attached to a sign of mass 10 kilograms. The pole itself has a mass of 1 kilogram, and then it's being suspended by a cable that's attached to it here at a distance of 1.5 meters, and then it goes up to attached to the building, and it makes an angle of 45 degrees with the pole. Very basic question. What is our object? What's the object in the problem that we're going to be considering the forces acting on it and the torques acting on it? It's the pole. The pole is the object that's not rotating. The net force must be 0 that's acting on it, and the net torque must be 0 that's acting on it. It's typically the first thing you really need to make sure that you understand. What's the thing in the problem on which the forces are acting and the torques are acting that's not rotating? And in this case, it's the pole. Let's draw in our forces. What forces are acting on the pole? Well, you can think about them. There's the tension in the cable. Where does that force act? That force acts at the point where the cable is attached to the pole. In what direction is that force? That's a tension force, and that force has to act along the direction of the cable. So that force is going to be up in that direction, and we'll call that T for the tension. What else? Well, there's the sign hanging on the pole. Where does that force act? It acts over here at the end of the pole. And in what direction is that force? It is downward that way. The sign is pulling down on the cable, on the pole, I'm sorry. Now in this case, the pole has a mass, and so there is going to be a weight acting on the pole due to its own mass. Where does that force act? That is going to act at the center of the pole. So at the center of the pole, we have to put in the weight of the pole, and we know that one is going to be straight down. Let's actually start putting some numbers in here as we go along. What is the magnitude of the tension? Actually, I'm sorry. I forgot to tell you what the problem was asking about. The problem is asking about, one of the things is, what's the tension in the cable? And then I'll come back to what else it's asking for in just a second. So one question is, what's the tension in the cable? So we can't put a number in that because we don't know what that is yet. That's one of the things we're looking for. Let's put in the magnitude of the force of the sign. The sign has a mass of 10 kilograms. The weight is mg, 10 times 9.8, 98 newtons. So this force is 98 newtons. The weight of the pole has a mass of 1 kilogram. What's the weight of the pole? mg, 9.8 times, or 1 kilogram times 9.8, 9.8 newtons. There we go. What else? Well, the hinge must be exerting a force on the cable, on the pole. The hinge is pushing it in some direction. We don't know. How is the hinge pushing on the pole? Is it pushing this way or that way or this way? We don't know. Rather than putting in a magnitude and direction for the hinge force, let's just immediately break it down into x and y components. That'll just make it easier for us. And if we wanted to, we could always put those components back together. So let's say that, and again, we're going to define x and y coordinates this way, x horizontal, positive that way, y vertical, positive this way. Let's define our hinge forces. we'll say it has an x component, and I'll just draw it in, h sub x, for the x component of the hinge force, and a y component, we'll say h sub y, that acts in that direction. The other part of the problem then is to figure out what's the force exerted by the hinge. What are h sub x and h sub y? Sorry, I should have said that right in the beginning. But actually we needed to talk a little bit about the force from the hinge before we could actually determine what we were going to look for. The problem is then, what is t? T equals what? H sub x equals what? And h sub y equals what? That's the question we're going to be trying to answer. Questions we're going to try to answer. There we go. How do we go about solving these problems? We've already done a couple of them, but let's generalize our approach just a little bit. These are what we call, we've talked about this before, these are a type of static problem. We've got to generalize our approach to static problems because now, in addition to having an object that is not accelerating, it is also not rotating. Before, when we looked at static problems, we could always say that the net force in the x direction was equal to 0, and the net force in the y direction was equal to 0. And those were our two conditions for a static problem, for an object not to be accelerating, and then typically not to be moving if it was stationary. We now have an additional restriction. For an object to not be rotating, we also must have that the net torque is equal to 0. These are our conditions for mechanical equilibrium. The conditions for mechanical equilibrium. In other words, for an object to be in equilibrium, essentially to be not moving, we must have these three conditions met. The net force in the x direction has to be 0, the net force in the y direction has to be 0. Now, if this were actually a three-dimensional problem, we would have an additional force restriction. What would that be? The net force in the z direction would have to be 0. Typically, we limit ourselves to 2 dimensions for these problems. But we then have a third condition, and that is the net torque has to be 0. In order to solve these problems, we'll basically go through these. The first problem with the seesaw, we didn't even look at the 2 force conditions. The second problem with the plank, we looked at just 1 force condition. But in general, we need to look at both force conditions and the torque condition, and then solve those for whatever we're looking for. Very, very good. Let's start out. We'll start out with the x condition equals 0, and then the y condition, and then the then the torque condition. We'll go through those one at a time, and let's see what happens. For the forces in the x direction, what do we have? What forces are acting in the x direction? Well, we've got h sub x, so we have F sub x equals h sub x. And then the only other thing acting in the x direction, or with a component in the x direction, is the tension. So the tension is acting up this way and therefore has a component in the horizontal direction. The x component would be this much here, which is t cos 45. But we notice that that is acting in the negative x direction. So we have minus t cos 45. The net force in the x direction has to be 0, so this all equals 0. Bringing this to the other side, we have h sub x equals t cos 45. What about in the y direction? What forces are acting in the y direction? Well, we have h sub y, so F sub y equals h sub y. The tension has a component in the y direction, and that would be this part, which would be t sine 45, and that is in the positive direction. So we have plus t sine 45. We then have the weight of the sine, and that is in the negative direction. So we have minus 98 newtons. And then we have the weight of the pole itself, which is 9.8 newtons, again in the negative direction. So we have minus 9.80 newtons. Again, all of the forces in the y direction must have a sum of 0. Total force in the y is 0. So this all equals 0. Adding these two together, bringing them to the other side, and we have h sub y plus t sine 45 equals 107.8 newtons. We can't go any further than this at the moment because we've got an equation with two unknowns. We can't solve that. We have another equation with two unknowns, a different unknown, in this case h sub y, so we can't even solve those yet. So let's move on to the torque equation. What torques do we have? To figure out the torque, what do we have to choose? We have to choose the location of our origin. Where are we going to put it? We can put it anywhere we want. But can we choose a point that will make it easier for us to solve the problem? Yes, we can. Remember, whenever we put the origin at a point where a force is acting, it removes that force from the torque equation. Notice that we've got two unknowns that are both acting at the same point. Why don't we choose our origin to be at the hinge, origin, and therefore both of those forces will give rise to zero torque. That would be a good idea. Let's do that. Choosing our origin at the hinge, what are all of the torques acting on the pole? What's the torque due to Hy? It's acting at the origin, so that torque will be 0. So I've got 1 0 in there. What's the torque due to Hx? Hx is acting at the origin, so we get another 0 there. That 0 is for h sub x. Torque due to Hy, torque due to Hx, both 0. What's next? What is the torque due to the tension? Remember, how do we calculate a torque? Rf sine theta. What is R for the tension? What is the distance from the origin to the point where the tension is applied? Well, that's 1.50 meters. So we've got 1.50 meters. Times the force. What's the force? T. What's theta? Now we've got to be a little bit careful. Remember, theta is the angle between R and F. For the tension, R is the vector that goes from the origin to the point where the force is applied. It looks like this. What's F? F is this angle. What is R? How do we, what is theta? How do we find theta? We have to put them tail to tail. Putting these tail to tail, that is R and F, tail to tail. What angle do we want? We want this angle right here. So theta for the tension is that angle right there. What is that angle? Well, we know that this angle is 45 degrees. That angle must be 180 minus 45 degrees. What's that? 135 degrees. Very, very important. Be very careful choosing those angles. I want to make sure that when you choose your angle, you choose the correct angle that's between R and F for whatever torque you're looking for. Even if there's another value that you could stick into sine and get the same number, I want to make sure that you get the appropriate angle for the way we have defined theta. Let's be consistent and use the way that we define angles between vectors, and then no matter what equation we use, we will always have the correct angle. In this case, 135. Is this a positive or a negative torque? Well, this is tending to rotate the pole in a counterclockwise direction, so positive. Great. Let's go on to the next one. What about the weight of the stick? What is R for the weight of the stick? Where does the weight of the stick act? It acts at the center of the stick. So what is R for the weight of the stick? It's going to be half the length, which is half of 2, 1. 1 meter. So for the weight of the stick, the R is 1 meter. What is F? 9.8 newtons. 9.8 newtons. What is theta? Theta, in this case, 90 degrees. So sine 90 degrees. Is this a positive or a negative torque? In this case, it's tending to rotate the stick in a clockwise direction, so negative. Last torque, the torque due to the weight of the sine. What is R for the weight of the sine? Well, that's going to be 2 meters. 2 meters. What is F for the weight of the sine? 98 newtons times 98. What is theta for the weight of the sine? Again, R, F, 90 degrees. So sine 90. Is it a positive or a negative torque? Again, the weight of the sign is tending to rotate the stick in a clockwise direction, so negative. There we go. Phew! That's a lot of torques. Multiplying out the 1.5 times sine 135, and we get 1.06 meters. Whoops, I'm sorry. I forgot the meters in there. 1.50 meters. 1.06 meters times t. Multiplying all of these out, adding them together, and we get minus 206 Newton meters. Bring that 206 to the other side, divide by 1.06 meters, and we end up with T is 194 newtons. Then take that T, stick it up in here. T cos 45 gives us H sub x, and H sub x turns out to be 137 newtons. Take T and stick it in our y equation, whoops, here, put it in here, and we can solve for h sub y, and it turns out that h sub y is negative 29.4 newtons. What does that negative sign mean? Well, that means that h sub y is actually pushing on the stick in a downward direction. Does that make sense? Why is it down? Well, yeah, it does kind of make sense. Let's think about this. Here, what's going on? We've got this stick that's supported by our cable, and we've got a weight over here, the sign, that's doing what? Tending to push the stick down. Well, look at that end. What happens to that end as I push this one down? That end tends to go up. To keep this stable, we would have to push this end down in order to support the weight hanging over here. So that makes sense. The hinge actually has to push down on this end of the stick to keep the stick from rotating up. The pole, to keep the pole from rotating up. Very, very good. And there are our final results. The results for the tension and the two components of the hinge force. If we wanted, we could put those together and find we've got a value here and a value here. We could find the net result and the angle, but that's okay. We're not worried about that. This is good enough, finding h sub x and h sub y. Very, very good. Let's take a look at one more torque problem like this. This is a classic problem. It's a problem of a ladder leaning against a building. What do I mean by a classic problem? What I mean is a problem you're probably going to see again.